uh, of ranging that we have implemented in the real system, right? So you can ask any questions if you have right now, or we will go through it, and in the end we'll have also a Q&A session. Okay. So initially, right, what we started with, I'm trying to recapitulate what are the things that we have already looked at, right? So we looked at a basic multilateration system where we sort of understood that how the ranges and the anchor information combined could help us in estimating the location of the node, right? So we kind of stressed 2 points, that this information about the anchors, right? The coordinates is basically coordinates of anchors. This needs to be known. Okay, this is a known thing that is required by our multilateration algorithm, and this is the ranges, right? The ranges from the device to the anchor. So do not confuse this otherwise. So anchors in this particular setting do not range among each other. So what happens is the nodes or the device that we are trying to localize is going to range with the anchor. So this ranges is basically your distance measurement, distance between your node or device and anchors. Okay. So this should be crystal clear in your mind, right? This is something that has been done in the first two classes, both with respect to GPS as well as in the second class when we studied multilateration. We worked on a demo and so on, right? So ranging and anchor information are the two things that will be necessary. And then, as far as ranges were concerned, we also understood, right, how non-trivial the process of ranging is. Right, it is not something just simply getting a timestamp from the kernel and then passing it on. We could see that how sensitive the range is with respect to the time of flight information. Okay, because we are not directly able to measure or estimate the range. What we need to do, we need to measure the time of flight, and only when we know the time of flight, that multiplied by speed of light is going to give us the uh, an estimate of the range or the distance, right? And for that also we saw how this low level wireless physical layer information, in particular CIR or channel impulse response, can give us an estimate of the fast path, right? The line of sight path or the shortest path, right? And these were the different taps that we mentioned within the channel impulse response. So it is a tap at 0, tap at 1, tap at 2, and so on. And I also told that this kind of information is often available in some of the radios, right? The radios can expose such information for a programmer to read. Okay, it is not always available. I mean, they don't always expose this information. Of course it is there inside the radio, but often they might not expose that information to the outside world. Okay, so in such cases, whenever they are exposing this information, we are free to look at the impulse response and also look at what the fast path is, right? We can estimate that. And there could be some radios that also gives you an estimate of the fast path, right? We will give you an index of the fast path, right? So maybe this is the fast path and it can give you an index, right? Or index of the first two or three paths that it thinks that could be the shortest one. Okay, so and we also saw what are the challenges there because of the inherent amount of noise that will be present in this impulse response. It is sometimes very challenging to know the index of the fast path. So we are kind of aware of what is the way we are getting the range and what are the uncertainties that could be associated with that range. And we also have one more information, is that what is the resolution of this impulse response in terms of the time taps, right? How close these time taps are. Based on that, I can actually uh, improve or make comments on the granularity of the ranging process, right? How granular the ranges are, right? So if you make a mistake of choosing this index 1 instead of index 2, what is the amount of distance error, or what is the range error that you are going to have. So index 1 minus index 2 gives you that distance, multiplied by speed of light will just give you the range error. Okay, so we know how to obtain the range and or time of flight directly, and then convert this into a proper protocol, right? Just the range might not be sufficient in that way, because there will be clock drips and all. So what we need to do, we need a process which is known as two-way ranging, and in particular, we looked at a protocol which is known as symmetric two-way ranging in order to calculate the distance in between the node and the anchors. Okay, and this calibration information is necessary because we had a discussion last day where somebody was asking about the location of the anchors being known, right? Yes, of course, sometimes it might become impractical, but there could be situations where you do an one-time calibration. Okay, you just, when you deploy the system, you just also associate those anchors to certain locations. Okay, and that will be hard coded in your multilateration algorithm, right? The multilateration algorithm is going to know where your anchors are. And we also looked at how do you solve such range equations, right? I spoke about multilateration earlier, so this is again multilateration. Okay, and we looked at a variety of different techniques how to approach this problem, starting from your linearization, right? Linearization, and then we also looked at LM algorithm and so on, right? So non-linear least square fit and so on. So today, what I'm going to do is that I'm going to take these ideas. Right now, I have a very clear idea about how to uh, about the engineering that goes under the hood for creating such range information. And you also know that given the location of the anchors, you can figure out the location of the device. So can we extend this idea in a realistic system, right? What I was discussing last day in a firefighting scenario, right? These buildings catch fire and we send troops inside, and we need to know the exact information of the troops' location, okay, or the firefighter or the first responders who go inside. We need real-time information about their location. So in case if they need fast aid or they themselves need to be rescued, uh, that could be done very efficiently. Okay, so that is one of the reasons we do require to track these people in real time, and unfortunately we do not have any good mechanism to do that, right? Because they might not have a map, and in that time, so they might not have always access to map, or even if they have access, it is not possible for them to look at the map physically and take the walkie talkie and tell them I am here, right? So that is really a lot of burden at that time when they are really tensed and trying to do all these rescue activities. Okay, so what kind of aid as engineers we can do for them, right? So that they could be tracked in real time, and that information could be sent out to the command center outside. Okay, so if there is any mishap that happens, I can immediately send my ambulance team or some other help, right, for rescuing them, so that we can ensure that the fatality among the firefighters comes down or they don't get injured so often. Okay, so what is the premises? You can think of a building like this which is on fire. It's a multi-storied building. The fire truck that actually goes there, the fire brigade people has arrived at that location, and we take help of a drone, right? We are going to tell you how this drone or an UAV is going to help us in order to track the people inside the building, or the firefighters who had gone inside the building. So we basically deploy the drone in that setting, and the drone goes up and starts hovering around, right? It is just going to go up the place where the fumes are visible. In this case, it goes to the fourth story or the fifth story height and starts hovering in that place. And what is required is some kind of a dashboard like this, like it could be a mobile app or a display in the mobile truck, where I'm going to zoom it up, right? So where the people who are outside, right, the command chief and so on, they could look at the building map and the real-time location of the firefighters, right? It could be possible that the building map is not available, at least in that case they will know which are the different directions of the building in terms of east, west, north and south, and whether two firefighters are close to each other or not, or whether they are far from each other or not. So I mean, even if the map is not available, I could still have a very good idea about their location. Okay, and what the drone does is the drone continuously sweeps this space, right? The drone flies around the building, and we are going to see that how flying around the building could aid in localizing this firefighter simultaneously. Okay, so that is the deployment setting. Okay, that is how we intend to deploy this thing, and now we are going to come why do you want to do a particular deployment like this and so on. Okay, so we have this wireless device, right, which is assumed that let us assume that this is the firefighter, right, or this is the first responder, this is the firefighter who is inside the building, right? And we, as you know, that in order to locate xy, what do we need? We need ranges and we need location of the anchor. Okay, so first, the first part, right, what we do is that we use ultra wideband, which is going to give you a very good distance resolution as well as good accuracy. Okay, so the accuracy could be in centimeters, and we have already seen that the granularity of that, right, the precision can reach millimeters, because it is tens of picoseconds time resolution in the impulse response. Okay, I think 15.6 picoseconds was the granularity of the impulse response, which probably translated to something like 4.7 millimeters. And the accuracy often, right, experimental data we have seen, right, it is often about 10 centimeters to a few tens of centimeters for ranging. Okay, so what you get here is the range. So now this is indoors, and this is like it could be a fifth story or the fourth story or a very high up, right? It's not very near to the ground, so we cannot have anchors placed on the ground, right? And other problem is that we cannot place anchors inside the building, because that is too much of a hassle for the firefighters. You cannot expect them to go inside, take the devices, right, take the anchors, deploy them, also note down their location. That is infeasible, that is not possible. So what we do is that we basically take advantage of the 3D aerial space outside, because that bounding box that I have drawn is basically the walls of the building, right? And then there could be windows and so on, right? So this is basically your building, and we are taking advantage of the 3D aerial space, right? And UAVs or drones becomes an attractive option, because it can give you this uh, reference points for the anchors. Okay, so as I show you in this animation, right, so the drone itself could hover around, and this could cater for all the different anchor locations. Okay, so imagine that the drone also has this ultra wideband radio, as like the uh, firefighter. So the drone also has this UWB radio, right? And that is going to range with the firefighter continuously. Okay, not just one firefighter, but many firefighters, right? So depending on how many people are there inside. So that is the scalability bit, right? How many we can range at the same time or within a certain time. Okay. So hope the motivation behind using drones is clear, right? Why do you suddenly want to use drones in such a setting? Okay, and one more thing is that you can also add diversity, right? Sometimes if we just restrict ourselves to 2D, even the anchor is in 2D, so at certain locations, maybe here you have certain obstacle in between the building and your drone. Maybe there's a big tree, right? Maybe this portion, there's a tree that is blocking your view, or basically going to add to the non-line of sight path, which is basically going to have some kind of multipath error, right? So in that case, what you can do, you can simply elevate the drone or make the height of the drone lower, right, such that you have a line of sight access, right? Um, or we don't have any other clutter in between the building's wall and your drone's location, right? So that is also possible, and it could be automated, right? By looking at the impulse response data, you can sort of understand that what is the multipath that is present in that environment, and based on that you can adjust the height of the drone. Okay, so these things are possible. So your the trajectory of the drone could be just a function of this multipath environment. Okay, so that is possible, right? We have not implemented this in this particular system, but these are the things that you can think of extending such systems. Okay, so if you have like a research mindset and you want to really delve more into such data and how do you want to control, let's say, the drone based on such data, these are like open things that you can try out. Okay, so again, coming back to the precision, we already kind of discussed this earlier, that the precision depends on the bandwidth of the signal and basically the time resolution of the transmitted pulse and received pulse. And because it depends on the bandwidth of the signal, we had to choose something like an ultra wideband, which gives you tens of centimeters of resolution using a gigahertz kind of a bandwidth, right? We could have used this Wi-Fi thing, right? 802.11 MC fine time measurement, right? I don't know how many of you actually have gone through the documentation or some of the tutorials that were presented, right, yesterday. And I asked you to look at the Android APIs, right? The developer tools that are made freely available, and you can try these things out. Okay, so you could have used this, but the main problem that would happen is that your ranging itself would be having some meters of error. Okay, just for the range, right? And then you will have the location tracking done, right? So that will also bump up the error to a very high uh, margin. Okay, so ultra wideband is going to give you a good trade-off in between the range resolution. So the range resolution is in tens of centimeters, and also you need to see that what is the range and the penetrability, right? Range means what is the absolute value of the range that you can achieve, right? What is the maximum distance? What is the maximum distance, right? And often, since we are talking about indoor locationing or indoor positioning, because the firefighters are deep indoor or inside the building, you need to penetrate much inside, right? So the signal has to go through the walls, or if there is a window it can go, but there are internal walls inside the building also, right? That is going to cut down the distance your signal can travel, right? So if you take some technology, let's say if you just start using millimeter waves, right, which is like at a very high frequency, and it can give you a very nice resolution in terms of range, right? But it is not going to travel far. It's just going maybe inside a small room, it is fine, but you cannot use this in this scenario. Okay, so let us see how the solution works, right? So the drone actually behaves as a mobile anchor. Okay, so the UAV is going to collect as many ranges as possible over time for all the nodes, right? So I'm just going to show you the example using one node, but it applies to all mobile nodes. So the UAV collects many ranges over time, and the trajectory, it's basically forming something which is known as a aperture, right? It's a synthetic aperture because it's not coexisting in real time, right? It's a temporal aperture, right? So I'm saying that the anchor is here, but the anchor is not here simultaneously, right? After some time the drone is going to fly to these locations. Let's say this is location 0, and let's say this is location k, right? So the drone is not going to coexist in location 0 and location k simultaneously, right? It is going to fly, and it will take some time for the drone to travel from L0 to Lk, right? And this aperture will be formed temporarily. Okay, so imagine this as a replacement of many anchors which are just deployed, right? You can always imagine that. So L0, L1, L2, L3, dot dot dot. Let's say this is Ln. So as if I am replacing n anchors placed in the air by this synthetic aperture. Okay, it's an array of anchors, right? And we will see like what, of course this is good in the sense you don't have to have many anchors, and that is kind of infeasible for us to do. But this drone thing can also bring us more challenges, and we are also going to look at what are those challenges. Okay, so it works fine for static nodes. Okay, so as long as the nodes are static, it doesn't move, it works fine. Okay, So what happens when the drone starts moving? Because that is the immediate next question that you will have, right? The nodes are mobile. So whenever it is mobile, the range that you are collecting when you are at location L0 and the range that you are collecting whenever you are at location LK, they are very different. Okay, different in the sense different given the location of the node, because the node's location has changed. So at the time when the drone was at L0, you have collected a range R0, and this was corresponding to the location of the node. Let's say that is X0 comma Y0. However, whenever you are at LK, right, the anchor location or the drone location has become LK, and you have collected the range RK, right? Your node's location has also become XK, YK. Right? The node is not assumed to be static. So if you simply apply multilateration on the data of these LIs, right, plus the RIs, so range information and the location information, and this goes to the this multilateration MLAT, let's say, right? So the estimate of XY that you are going to get, right, this is completely garbage, because there is the equations that you have supplied to the multilateration system is inconsistent. Okay, the equations doesn't make any sense, because these equations are not going to find out any unique value of xy, because every equation was recorded at a separate state of the node. Okay, the node itself is moving, and however we designed the multilateration algorithm was is not going to work directly, right? So this is a primary design challenge. Next is, what about turns, right? The nodes could take turns, right? And we are not catering to such needs. It could move not only in a straight line, but it could move in a carved path, right? Maybe if it is moving in a straight line, there might be some possibility to do some interpolation and know that okay, it has moved and so on, right? It could actually make turns and go in a completely different direction. How do you know that? Okay. And the third challenge is that I told you, with such techno like such signals will have a limited penetrability. Okay, it cannot go infinite distance indoor, like, or hundreds of meters indoors. Okay, so you have to come up with a systems methodology to cater for this limited reachability problem, right? How do you reach deeper inside the buildings in this particular context, right? What do you do to achieve that? Okay, so let us come to this thing one by one. Let me some issues with this. Okay. So first, we are going to look at the nodes mobility problem, and what the proposed solution in short is basically solving for velocity instead of solving for location. If we solve for velocity and then assume that let's say the velocity or the speed, average speed, was sort of constant, then we can take help of kinematical equations in order to solve for the location of the node. Okay, so just coming back to the notations here, CXI, CYI, and CZI are the location of the drones or the anchor. So this is the drone location. Okay, or basically it is proxying for the anchor. And these are the node location. Okay, node or the firefighter. Okay, this node is indoors. Okay, so this is a setting. And what is the value of Ri? Ri is the range that is taken in between the drone and the node. So CXI, CYI, CZI, right? These are the drone locations, and XI, YI, ZI are the node locations. Okay, and again, we still get a smell of how we tried to solve for the case of multilateration, how we set up the nonlinear least squares, that formulation, right? It is very similar if you see. Okay, so just that there is only one catch, is that this xi, yi, and zi keeps on changing continuously. And if we have an assumption that the velocity is uniform, or like we are assuming some kind of an average speed in the x direction and y direction, that is what we denote as vx and vy. Okay, so vx is the average speed in the x direction. So this is the average speed in direction x. Okay, and similarly Vy is the average speed in the y direction. So average, so this is Vy speed in direction y. Okay, so now if I know that, and if I know, let's say the guy started from x naught y naught, like x0 y0, I can always write this equation as xi is equal to xi minus 1 plus vx into delta ti, because I know what is the time that passes in between these two range procedures. So there is ri and ri plus 1. I know what is the delta t that has elapsed in between these two. Delta ti I know. Okay, because I am doing these range measurements, I have a timestamp for that. So I know when ri was taken, I know when ri plus 1 was taken, so I know this delta ti. Okay, and let us assume that that guy had a velocity of vx in the x direction and the velocity of vy in the y direction. So I can aram se write this equation. Okay, xi minus 1 plus vx into delta ti, yi minus 1 plus vy into delta ti. There is no harm in that, given kind of assumptions we have made. And we can use this recursively and basically come to this point where I have the first unknown, x naught, y naught, or x1, y1. It depends on what kind of index you are using. And then these are the two extra things that we have assumed, vx and vy. Okay, so now there are four unknowns. Earlier we were having two unknowns, x and y, and now we are having four unknowns. Okay, and note that this is again has become a linear equation, right? Xi is equal to x1 plus vx into this. Okay, but these are the expansions of xi and yi which are going to go in this equation on the top. Okay, we still have to solve the nonlinear least square problem. It's just that instead of having a single value, right, x naught, y naught, that we had in case of a regular multilateration, regular MLAT, currently we don't have this x naught, y naught. What we have is you have x naught, y naught, that is a starting position, but you also have to solve for this vx and vy. Okay, so there's a modified version of this MLAT. Okay, and what you need to basically solve for is, let me erase this so that you can clearly see. Okay, it is argmin f, right? We are trying to solve for the we are trying to minimize this cost function f, such that we are trying to find out the values of x1, y1, vx, vy, and we are minimizing this equation. This equation is very familiar to you. This is the Euclidean distance square minus the range estimate square, and ideally if the ranges were perfect it should have been 0, but it's not the case, right? And we do not have just three anchors. The drone moves in this aerial space, so the location of the drone is known from the GPS, right? And if there are n such locations, right, there could be n such points in the synthetic aperture that we are considering. That's why I have varied the location from 1 to n. Okay, it starts from the first location, location number 1, and it goes to location number n. And for all such locations, I have recorded the value of cxi, right? Cxi, cyi, czi. Czi is basically your altitude, right? And cxi and cyi are your lat and long, right? So that can be directly obtained from the GPS. Okay, any of these drones will have some kind of a location tracking system, otherwise it will not be able to fly. It has to know that in the 3D space where it is, right? It could either be through GPS or any other technology like camera or any other nodes that we have to, like beacons kind of thing that you have to put on the ground, right? So for the drone to fly you do need some kind of a location infrastructure, and that is often inbuilt in the drones. Okay, so hope this slight modification of the MLAT problem is clear, right? So that is how you translate your learning. You have learned the regular vanilla version of multilateration. How do you extend such techniques in order to solve such problems, right? So this is a example of a real life problem. You might face other problems, and now you have to be creative enough to actually have good understanding of MLAT, and then how do you tweak such standard technique in order to solve your own problem. Okay, so now you see if we see naive multilateration, which is shown as the green bar, right? I have almost 3 times or 4 times, right? In this case, when a person is running, right, so that the velocity is high, right? So it keeps on getting smeared very easily. Uh, in that case, I am almost getting like 4 times improvement compared to uh, our technique that we have proposed and known as track IO, right? Tracking inside out, right? That's what track IO means or stands for. Okay. And I would ask you a question here, right? If the person is stationary, if the person is not moving, our algorithm does pretty poorly. Okay. So this performs poorly. Okay. So my question is why? You have gone through multilateration, you have gone through the explanation that I have given in the previous part, right? If you have any confusions, please ask me. But if you have a good idea about what has happened till now, right, you should be able to have answer this question, right? Why in a stationary case the error bumps up, right? The naive multilateration works better. Okay, so somebody can come forward and try to answer this question.
Sir, actually in the UMB, sir,
Sorry.
there is again 10 centimeter, there is some deviation is in.
But that is
Deviation
true
is
for all the cases. The 10 centimeter range error is true for all the things, right? And it is also true for both these things in both them, right? What is different? The drone is the same, the GPS is the same, the hardware is the same, the range error is the same, right? The technique is different. What is this technique doing such that it is very good for the non-mobile, for the mobile cases, and it suddenly becomes poor in the static case? Okay, I'll just give you the answer, right? So I mean, this kind of things you have to like, if you answer these questions right, you will have, and you can think that at least you have a good understanding of what was going on, right? Maybe you will pick up, right? You will go through these videos and try to look up other
Because,
materials.
sir, the longitude, latitude, and everything is again become static, sir.
Longitude, latitude of what will become static?
Altitude, this particular stationary object, sir. Here.
A stationary object does not have any GPS, right? It is basically the firefighter who is inside the building.
Okay, sir.
So latitude, longitude is only associated with the drone, right? So
Okay.
latitude and longitude is basically the GPS. Indoors, you don't have GPS. We are trying to find out the location of the guy.
Okay.
So the simple answer is that, see, this is in one word. What is going on is known as overfitting. Okay. We know that Vx is equal to 0 and Vy is equal to 0, and we ask the system of equations to solve for that in spite of knowing that Vx is equal to 0 and Vy is equal to 0. Okay, so it will artificially try to fit some value of Vx and Vy, and simultaneously x naught and y naught, right? So we are assuming that these are all unknowns. Okay, but we just left the system of equations in the same way in spite of knowing that the person is not moving. So what it will try to do, it will try to artificially fit some values of Vx and Vy that might be non-zero, right? It might have a lot of local minimas, right? And some combination of x1 y1 Vx Vy is going to satisfy that, right? So it might get stuck in some kind of a minimum. Okay, but in case of a static scenario, I already know that Vx is equal to 0. Okay, so this extra thing is just going to introduce some kind of an overfitting, and that is the reason why magically whenever you are starting to have a non-mobile like mobile scenario, your naive multilateration works poor, right? And just the instant whenever you are stationary, right, the node inside the building doesn't move, your multilateration, naive multilateration works so well. Okay, so you can have different techniques. You can know proactively by using an inertial sensor, IMU, whether your movement is 0 or not. If your movement is 0, you actually switch to naive multilateration. If you are actually moving, then you can just use track IO. So the next problem is with tackling turns. Again, it is related to how we try to solve for this multilateration thing, right? We are again going deep inside some artifacts of this multilateration technique in order to understand that a turn has happened. Okay, so first let me explain why the why basically the uh, what is the role of the synthetic aperture here. Okay, so we are trying to use an adaptive aperture that we will come later, right? What is the smaller aperture mean? Smaller aperture means that the geometric diversity that we have is less, right? Think about three anchors that are placed close to each other, right? We saw a demo, right? And if we just have these three anchors just placed to close to each other, and you have the node here, right? The geometric dilution of precision will be very poor. Okay, so if you have a small aperture, small window, okay, this is going to result in a very poor geometric dilution of precision, poor GDOP, which basically means poor location accuracy. Okay, so what is the good part about it? The good part is that we actually store less historic data, right? Because this window is actually a sliding window, right? So the drone moves, right? So this is like 0, this is 1, this is 2. Next it will become 3, 4, 5, and so on, right? As the drone moves. Now, from 0, 1, 2, the next window will be, let's say, 1, 2, 3. The next window will be 2, 3, 4, and so on. So at the same time, even if we have a poor geometric dilution of precision, we are also having less historic data. So whatever bad things happen, this data gets quickly trimmed off. Okay, so maybe the drone, maybe the node has moved, right? But again, we are not considering very old data. Okay, so we are getting rid of old historic data. Okay, that is why it can quickly adapt to velocity changes. Now in the next instant, if it turns, okay, the probability that we will have stale data which caters to the direction or heading in this side, right? Let's say north side, will be less, right? And you will have more data which is basically catering to the east side, because you are having less historic data. So you are trimming off the stale data continuously. And what is the other extreme? The other extreme is having a very large aperture size. So this is your synthetic aperture, right? The way this drone moves. So this is 1, 2, 3, 4, 5, 6, so on. Maybe this is 20. So now your aperture is of size 20, which is basically a larger window, larger window, uh, and that gives you a good GDOP. Okay, but you are retaining the history. You have more historic data. So whenever you are taking certain decisions and moving in a different direction, let's say you are coming in this direction, right? So maybe up till here, you are this is south, right? Up till here you were collecting data that were pertaining to the south, and suddenly you made a movement towards east. So all the data from this onwards, okay, till 20, right, should be pertaining to the east side movement. But my system doesn't know. Okay, and I am using this entire stretch of data from 1 to 20, which consists of a combination of southward movement and eastward movement. Now I'm confused because it will adapt very slowly to the velocity changes. Only I have to flush out. So this has to be flushed out. If it is there in the system, it is going to create erroneous results. So we make an observation here and then try to adapt our aperture size. Why do you need to adapt? Because whenever I think there is an error, I need to shrink the aperture, because I need to flush out this data from 1 to 6, right? So this part of this thing has to be flushed out. I don't need, whenever I have detected that the person has taken a turn and moving in a different direction, this data is going to be inconsistent, because I have assumed that there is a constant Vx and Vy. I cannot assume that suddenly there is the Vx has changed and Vy has changed. right? So your equations will become again inconsistent in terms of Vx and Vy also. Okay, so hope this is completely clear. Okay, if you have any questions, please stop me, ask me the questions. Okay, so now how to detect a turn? Okay, so we are trying to detect the turn by looking at the solver's residual. So if you have looked at the LM fit uh, algorithms, right? The way the library or the LM algorithm, right? What we are trying to do, we are trying to minimize that function argmin. We were trying to find out, in this case, x1, y1, vx, and vy for a certain function f. Okay, and we are just trying to minimize that thing, and we will try our best to make it zero, but it might not be possible. It might not end up getting certain suitable values of these things that will make f zero. Okay, but we can register how much we were able to solve this problem, right? How minimum we could make it, and that is basically known as the solver's residual. Okay, the residual might not be zero, but residual could be some quantity which we are trying to minimize. And if the solver's residual is close to zero, you can think that you kind of have approached towards an optimal solution. Okay, but if it is far from zero, then the solution is not optimal. There is some error associated with that. So that is how we basically try to look at the reliability of the turn detection. Okay, we want to detect when the person has gone straight and taken a turn. We want to identify this instant, identify this time instant. If we can identify this time instant, we can ignore the range values here, ignore everything here. Okay, this can be ignored very easily. You can ignore this data because this is going to screw up the solution. We can only use this data. Okay, so see, I have also shown the errors correlation with the residuals, right? So this is x-axis is time, and y-axis on the left hand side is the location error, and y-axis in the right hand side are the residuals of the when we try to solve that equation, that non-linear equation. When you try to solve, what is the value of the residual? And you see that if you have a location error that is close to zero, like lower values of location error, the solver's residual is also less. Solver's residual is also less, right? Less. So less error is directly proportional to, or at least correlated to, if it is not proportional, it is correlated to lower values of the residuals. Okay. So whenever I could detect a spike, whenever I could detect that there has been a spike in the value of the residuals, I can flush out the old data and start using the aperture afresh. Okay, so solver's residual is less in two cases, and I can detect a turn because now the with the old heading, right, the solver's residuals have suddenly started increasing. Okay, so I detect that there is a turn in that point in time. Okay, and this is going to result in higher residuals error. And if I just refresh the window, okay, if I refresh the window, then my solver's residuals are going to come down and I am going to have better accuracy. Okay, because this is a window, I just reset the window, and then it starts building up the history again from scratch, and slowly it is going to go better and better and then become very good. Okay, so this is a way we leverage the residual of the solver in order to detect this turn. Okay, so just find out the turning instant based on where the value of the residual starts picking up. So the third problem that we had with limited reachability was with this multi-hop ranging. So what we can do is that instead of just ranging directly with the nodes which are far in the indoors, right? We try to first range with the guys which are in the front, right? So the nodes which are in the first hop, I call it, because this is directly reachable from the UAV. Okay, and this is not directly reachable. So what we do is that we try to directly talk to the first, in this example, the three nodes 1, 2, and 3. Okay, and once we know their location, uh, node number 4 is going to be localized using 1, 2, and 3. Okay, and you have to modify the TWR ranging algorithm, right? It is not just going to be uh, a simple TWR, right? So TWR can give you the range in between four, like these individual links, right? It can give you this RI, but how to orchestrate this entire system as a whole is some interesting problem. And if you are really interested, you can look up the paper. It's all online, right? You can look up the paper and see what we have done. Okay, why it is a challenging problem, right? See, 1, 2, and 3 are continuously changing locations. The drone is continuously changing location, because if the drone is static and the nodes move, right, I cannot have any clue, right? Because anyway, the nodes being mobile makes it a very difficult problem. So now on top of that, 4 also moves, right? And 4 has to be ranged with 1, 2, and 3, and in order to get the locations of 1, 2, and 3, the drone has to move. So nothing can be simultaneously done, because it will create interference, right? So there is a time slotting, and everything is just going to follow a time slot. Every range is going to follow a time slot, and this is strictly TDMA, strictly time division multiple access, right? Otherwise you will face interference. You cannot have multiple ranging done in the same time slot. That makes this problem very challenging. It is does not scale that easily. Okay, so that is what I call hop 1 and hop 2. And the good news is that, like I show a real example where we deployed the system, is that we could cover an area of almost 1300 square meters on one side of the building. And if we need something here, so this was, we were not able to cover out. This is outside our coverage. So what you can do, you can even deploy a second drone on the other side. Okay, this is a really big building, right? Whatever we have covered is already 1300 square meters. Okay, this is a real example of the hardware. And if you are enthusiastic about building such things, right, it is all made of off-the-shelf components, right? And this is me. We are like inside the building. We have this ultra-wideband beacon I'm wearing on my head, and we were tracking ourselves. And the drone basically moves around, and in the app you could see where am I inside the building. Okay, so this is basically the hardware. We have a simple off-the-shelf DJI drone, and you have this ultra-wideband beacon, and then you have a Raspberry Pi which has the GPS, right? So we did not have to interfere with the computer inside the drone to get GPS coordinates. There are some of the advanced drones that give you those things, but this is a very simple drone. Okay, so we did not interfere with the internal hardware of the drone. We just simply used off the shelf components and put it together, right? So we have a GPS, we have a Wi-Fi in the Raspberry Pi that sends out the data, and the Raspberry Pi is also interfaced with the UWB chip, and this UWB chip is running the two-way ranging algorithm, and the TWR is also running on the UWB placed on my helmet. Okay, so in that way you can continuously range. I can also know the GPS location of the drone. So this basically becomes the anchor, right? This anchor is basically now a mobile anchor. Okay, so it's actually, we demoed it, right? So in the US we took it to actual firefighters, right, who did an extensive drill based on these devices, right? So they actually attached these devices, and we made it a little bit better. We put it with a smartphone, and they can took they took these smartphones with this beacons in their pockets, right? And once they are outside, the fire chief in the drill could directly see their location. And our drone, I did not show you that in the picture, the drone was moving outside. Okay, so that was a real demonstration. And the system wise, right, if you see, there is nothing very complicated that you can't do, right? There's a This is just a drone, and many of the universities or the colleges today, there are lots of students who are enthusiasts about drones. Just that I put a ranging modality or the ranging sensor like ultra wideband on the drone, and then there is a Raspberry Pi and GPS that is very easily available. Okay, there is no more hardware that is there in the system. Okay, so everything that runs, that all this algorithm runs in the Raspberry Pi. Okay, so any questions relating to this?
Sir, I have one question.
Yeah.
What if the velocity of the firefighter changes when he's not taking a turn? As in, he was walking and then if he suddenly starts running?
So then it will cause a problem, right? So what will happen is the solver errors are going to go up, right? So you have asked a very good question, right? Where it is not turning but suddenly change the velocity, and it is going to violate our assumptions of Vx and Vy. You are saying that Vx and Vy itself changes, right? So you are actually bringing in an acceleration component. So we haven't tried that, right? What happens in it is going to overfit a lot. So you can also have Vx and Vy and Ax and Ay. So mathematically fine, right? But in a practical system, often the concept of average speed is better in such scenarios which is dealing with human beings. We are normally walking at in between 1 to 2 meters per second. That's all, right? But if you are trying to track a robot whose velocity can be 1 meter per second or even 5 meters per second, then you might have to consider whatever you are saying. Let's say you want to also have an additional acceleration component that you want to solve for. Is that clear?
Yes, sir.
It's
Thank you.
just because of practical reasons we avoided having X and AY because it started overfitting more and we were facing more errors. In that way, it was more humble to just use Vx and Vy as a constant average speed.
Okay, sir. Thank you.
Anything else?
Sir, I wanted to ask, sir, how
Yeah.
robust are ultra wideband signals to heat temperature when during the case of fire?
It does depend a bit, right? So primarily some of the propagation properties, right, at very very high temperatures might be affected, but we are again uh, the errors that are going to happen, right, is will be can be compensated because the GPS itself is going to have some error, right? The GPS is going to have some meter level error. So although it might not be in centimeters, the ranging precision might not be in centimeters, but it is not going to exceed something like a meter. Because think about it, the
Okay,
ranging
thank you.
error, I am not complaining. The ranging error could be in centimeters, but here the anchor location has an error. If you have identified it, right, the anchor location is derived from the GPS coordinates of the drone, so that has an error, right? Okay, yeah, thank you.
Thank you, sir. Thank you.
Okay, so let me go to the next part of the
So,
tutorial. Yeah, tell me.
uh, yeah, so the algorithm that has been developed. So, is this these are open source so that we can play with them in our own experiments?
The algorithms are there in the paper, right? But the code that I have developed was done as a part of a company contract, right? So since I'm not even there, I don't have legal access to the code, right?
Okay.
Yeah, but the algorithms are whatever I have told you, right? It is very simple. There is nothing more than whatever I have told you there, right? So you can simply implement this idea of this equation, right? So if I go back, this is your objective function, right? Whatever I have written in the bottom,
Mhm.
right? So this is your objective function. So the main challenge is here is not this part, right? But putting this entire system together such that it works in real time, right? So you can solve this optimization function. You can write code this up if you have good idea of this LMFit library. Using that, you can do it in 30 minutes, right? It's not an issue. But how to actually have this entire real-time system set up, right? So that is where the challenge comes, and that is more of a system integration challenge.
I'm more of interested in that. So, uh,
Yeah, so if you're interested in that, ideally you should like take the pains to implement it, right?
yeah,
So that is only going to improve your skills on system integration, right? There are lots of unknown things that we cannot anticipate from these slides. When you start actually getting your hands dirty with starting to implement these things in a real system, you'll see hundreds of things will not work.
true,
Okay,
sir.
so why it is not working? So that those are different things which I cannot discuss as a part of the short-term course, right? There are many things that will actually take a long time. in order to discuss all those things. Okay, so I'm trying to improve the breadth, right? What are the different technologies there available? You can take these pointers and start exploring yourself, right? And I'll try to, if you have any questions, please feel free to ping in that Google groups, right? I'll try, if I have an answer, I'll try my best to give you an answer. Okay.
Thank you, sir.
Sir, if I can ask one more question. So, sir, does the architecture of the building, will it affect the velocity of the drone that will be chosen or the number of drones?
So this is a very interesting question. These are all intertwined, right? So the architecture of the building very much dictates the accuracy that you will get, because the
Yes.
architecture of the building is going to tell you that first of all, how much non-line of sight or what is the amount of multipath that will be present. Number one. Number two is the architecture of the building. If you think of the dimension of the building, probably that is what you are asking, right?
Yes.
So not only just where the walls are and where the corridors are, where the rooms are. If you think about the dimension of the building, note that the drone has to cover that entire span. The synthetic aperture should be good enough or big enough to cover that span, right? So what
Yes.
you are absolutely right that you have to improve the, like, increase the velocity in order to cover that entire span within a fixed amount of time, because those nodes inside are also mobile.
Yes.
So you can create, like, in terms of like an analytical interest, right? If you have the velocity of the nodes indoors that are bounded, let's say I don't want to go, the max v is, there is something called vmax of the nodes. So given the dimension of the building, what should be the trajectory or what should be the velocity of the drone? That itself is a research problem. How do you want to move? The drone should move in a straight line, or the drone wants to move in a circle, or the drone wants to move in some kind of a helical path. That itself is a problem. Okay, what kind of trajectory of the drone at what velocity gives you the best GDOP for a non-static scenario? The GDOP here you are calculating not with respect to a fixed node. The node itself is mobile, right? So this problem, if somebody is interested, you can, like, look at this problem, right, as a research problem. There are some pointers, right? People have tried to solve something similar, but not in a localization context. Okay, so
Okay. Thank
yeah,
you.
yeah. So this is, we are going to look beyond TOA. So TOA is like highly used in many real systems, time of arrival, and that's why we put a lot of time here. And now we are going to look at other techniques also that exist and what are the pros and cons that are associated with those techniques. Okay, so now we are all aware, just trying to revise. We had this, sorry, it's TWR, right? Two-way ranging. Let me change the ink color. Uh, Two-way ranging. So we had the two-way exchange in between the device and the anchor, right? So device speaks out something, anchor says something, again the device speaks out something, anchor says something. We went through this process yesterday, right? How this multi time, this, we are talking among each other multiple times in order to derive the range using this two-way ranging. That is clear. Now what happens if we just simply assume that the device transmits? Okay, so if the device transmits and the anchor receives, what kind of things can happen? Okay, so this is just a broadcast. So then what will happen is I don't have to have a separate time slot for talking to anchor 1 and a separate time slot for talking to anchor 2. What I can do, I just simply broadcast an information, let's say hello, right? The device says hello, and all the receivers receive the same packet and they can compare the timestamps. Okay, so the device, if I just trying to rephrase one more time, the device broadcasts a message, the broadcaster signal, right? It says hello, right? And then it broadcasts, right? Every anchor is a receiver here, and they will be able to receive that packet. Okay, so what is the difficulty here? There is the anchors have to be synchronized. If the anchors are not synchronized, they will not be able to compare their timestamps, right? So I am assuming here the anchors are synchronized, and what they can do is that the anchor 2 is going to know that I have received the packet at time, let's say t 1, the first packet, right? The first packet, it has received a time t1, and anchor 1 is going to think that I have received the packet at t1 prime. Okay, note that they don't know when the packet was transmitted. Okay, so they are simply comparing that time, or maybe the packet's time could have been mentioned, right? So what they are currently doing is that anchor 2 and anchor 1 are synchronized among themselves, and what they are doing is that what is t1 prime minus t1, this is something that they're trying to do, right? So if the source time was known, then you can simply use time of arrival, right? But the source time is not synchronized with the anchors now, very much like we had the problem of this thing in GPS. Okay, in GPS the anchors were transmitting, but in this case the device is transmitting. Okay, so in this case I don't know the origin, right? The t0 is not known. Okay, so what it would ideally be the analytical formula for the time of flight in this anchor 1? T1 prime minus t0. Okay, and what would be this case in the anchor 2? T1 minus t0. So what these people do, the anchors, what they do among themselves, they basically subtract these two numbers, right? Basically t1 prime minus t0 minus t1 minus t0. What will this become? Simply t1 prime minus t1, right? They can simply do this thing. They can do t1 prime minus t1, which basically gets rid of this value t0. Okay, and what is t1 prime minus t0 multiplied by c? This is d1. Okay, and what is t1 minus t0? This is into multiplied by c. This is d2. Okay, so t1 prime minus t1 is nothing but d1 minus d2. Okay, hope that is clear, right? Is it unclear to anybody? Okay. So the infrastructure receivers, right, are all time synchronized. So that is what I am stressing, right? Because if you want to subtract t1 prime and t1, you need to make sure that all the anchors are following a common reference point with respect to time. Okay, so that is why you can simply subtract without any clock drifts and so on. And till now, right, anchors, the way they are synchronized is using a wired system, right? So I have seen written here, right, this reliable wireless time synchronization is still something that is being researched on, right? So how can you maintain this synchronization for a long time, because these anchors are individually very cheap devices. These are like simple IoT devices that will exhibit clock drift. They don't have any atomic clocks like the satellites had. Okay, so ideally what is often done today is that they are going to be connected to some kind of a let's say an Ethernet cable or some cable that can send or synchronize this timing pulses, sync clock. Okay, so if you deploy such anchors, now think about the hassle. You are deploying these anchors in the building, and you have to run a cable, a physical cable that is going to synchronize the clocks of the anchors. Okay, in that way they will have the common reference frame with respect to time. And you don't, the good part is that you don't have to have any relation with the device. The device simply sends out a beacon packet, right? And whenever this beacon packet is being received on the anchor location, the infrastructure side knows your location, you don't know. Okay, so they can know because they know the location of the anchors, and they know the value of this d1 minus d2. From that they can calculate the location of the device. Okay, so we will come to this thing, and why I was bringing up this TDOA. See, this is not time of arrival, this is the time difference of arrival. T1 minus T1 prime is the time difference of arrival, because individually T1 is the time of arrival, T1 prime is the time of arrival, but we don't know that, right? So actually T1 prime minus T0 is the time of arrival, or T1 minus T0 is the time of arrival. So this is your TOA. This is your TOA. But we don't have access to T0. So what we do is that this is basically your TDOA. And I will come to all these things in a short while. Okay, you understood the premises. Now, the transmitter is not going to receive, right? So this kind of an approach is going to significantly save your battery. Right? So if you are keeping your receiver always on, that takes up more power compared to if you are sleeping all the time and then wake up to transmit a packet. So that is much more battery friendly. Okay, so it is going to save a lot of battery on your side, but the only problem is that the cumbersome architecture of laying out wires and cables all around, right? So that becomes a cumbersome procedure. So now I have already given you the description of how things are laid out. RX1 and RX2 are going to receive the packet, and at timestamps T1 and T2. So now I have made this one as T1. It receives the packet at timestamp T1, and it receives the packet at timestamp T2. And I can know that the difference of these times is basically the time difference of arrival. That multiplied by C is going to give me D1 minus D2. Okay. So now my question is that what is the possible locus of this device? Right? Because if I told you from the last few classes that if I know that the device is at a location, is at a distance of D1 from anchor 1, right? So I could describe this as a circle, right? Because if the device is at a distance of D1 from anchor 1, so any point on the circle that has a radius of D1 could be a possible location of the device, right? Similarly, if the device is at a distance of D2 from anchor 2, this is going to describe this circle with a radius of D2, and the multilateration was basically trying to find out the intersection point. But now the problem is not exactly that. Now the problem is that I tell you not D1 or T2, I tell you that D1 minus D2 is known. I have told you that I don't know what the value of D1 is. I don't know what the value of D2 is, but I know that D1 minus D2 is this. D1 minus D2 is K. Question is, what is the possible locus, right? Or what is the possible set of points that the device can, the device location can assume? So what are the possible, like you guys start thinking, possible set of locations for the device? Anybody wants to answer? If D is constant, circle. D1 minus D2 is constant, what is going to be the locus? This is like a +2 question, right? 11th standard question. It's coordinate geometry. Just recall. Anybody wants to come forward and answer the question? Sorry, I cannot hear.
Ellipse.
Ellipse. Can you repeat? Did you say ellipse?
Ellipse.
Yeah, sorry, it won't be an ellipse.
Parabola.
Parabola. So parabola has one quadratic term and one linear term, right? You have to have
Parabola.
Sorry,
Yeah. Sorry.
cannot hear you, sir.
Parabola. Okay.
Parabola has one quadratic term and one linear term, right? And in this case, you are basically computing the Euclidean distance. Both will be squared, right? There is no preference of x square over y or y. So you'll have x square and y square both. Right? So you tried out all sorts of conic sections, but it's actually a hyperbola. Okay. So if the difference of them is constant, it's a hyperbola. If the sum of them is a constant, it's an ellipse, right? Because if you remember, right, we used to study this thing in school, right? So you have these two, let's say, focus points A and B, and let's say you take a string, right, and this is a thread, and you put a pencil here, and you rotate this. So this is what the length of the string is constant, right? So let's say D1 and D2. So D1 plus D2 is the length of the string, which is constant, and you can rotate this. This is going to become an ellipse. But in our case, this is not D1 plus D2, which is constant. D1 minus D2 is constant, and basically this gives you a hyperbola. Okay, so I can show you how this thing works, right? So see, I have plotted all the points that are going to be on the locus. So even every time d1 minus d2 is equal to 8, and r1, rx1 and rx2 are the location of the anchors. Okay, is it clear? Okay, so analytically it's just some kind of excess Euclidean distance, the difference of Euclidean distances. You inherently have something of the form ax square minus by square, right, which basically leads to hyperbola. Okay, so this is going to be the locus, and then you will have multiple such hyperbolas based on the number of different time difference of arrivals you have, right? And the solution is going to be the intersection of these hyperbolas. Earlier we are having an intersection of circles, right? So we are having 3 circles that were intersecting with each other. Now we are going to have 3 or 4 hyperbolas that are going to intersect with each other. Okay, like this. If you have these 4 anchors, right, and you basically compute 2 TDOA values, it is going to intersect at some location here, right? And that basically gives you the location of the device. Okay, is it absolutely clear? Why is the locus a hyperbola? Maybe you can write down the equation and think about it, right? Write down the equation in the form of, you have the location of the device as let's say x naught y naught. The location of the anchor 1 is x1 comma y1. Location of anchor 2 is x2 comma y2. Okay, what is d1? D1 is equal to, all of you know, x1 minus x naught square plus y1 minus y naught square, right, root over of this. You have an idea of what d2 means, and you have an idea of what is d1 minus d2 is equal to some factor k. Write and expand this equation, and basically try to, everything here is known other than x naught and y naught. Okay, so this is a function of x naught and y naught which is going to describe a hyperbola, and my suggestion is please try to do it on your own and plot it, right? So that will give you a better insight of how the system is working. Okay, and here I have multiple pairs of TDOA values that are plotted. So there could be there could be multiple such hyperbolas that are intersecting with each other, creating this solution. So now, what are the limitations? Any idea about the limitation of such a system? A system limitation, right? What happens? What particular thing is difficult when we follow such a norm of locating the devices? The device is transmitting and the infrastructure receives, and the infrastructure does all the job for you, which is good, right? What particular scenario it will be difficult for you to deploy a system like this?
There is a line of sight. So means again, if they are not straight line.
Okay, I mean that is there. I mean that is a common problem that will be anywhere, right? In any sort of ranging procedure that is there.
Okay.
Anything that is unique to this particular approach, that is going to be a problem. See, the device is transmitting, that is giving you a lot of hint. Okay, because
So
I have
yes, sir.
Yeah, tell me.
So if there are multiple devices,
What will happen?
so maybe the signals they get mixed up.
What
Like
is
the
it known
signals
as?
going from multiple
What is it
devices.
known as? Signals getting mixed up. What can you tell me? What exactly it is known as?
So interference.
Interference. So you should not allow interference, right? And that is the reason I just 2-3 slides back I spoke about TDMA, right? So that is how you are designing the MAC, right? The medium access control has to be designed accordingly. So you cannot allow multiple devices to range simultaneously. whenever my device 1 is broadcasting, device 2 has to keep its mouth shut. Right, so you have to enforce some medium access control such that not all of them talk simultaneously, otherwise it will interfere, and interference means it is just going to collide and nobody is going to hear anything. Okay, if it is like random access. Okay, like for example, you have all studied aloha and things like that, I'm assuming, right? So they are just going to, nobody is going to hear anything. Okay, so that is the problem with this thing. The device is not, the system is not going to scale. Is exactly what you have indicated. Is if you have multiple devices like this, who is going to control them? If you have hundreds of devices, the first guy takes a turn at time t0 and the 100th guy takes a turn at time t100, right? So the duty cycle of the location updates is going to be cut off, right? If I need some kind of an SLA, right? So the service level agreement, the SLA is, let's say I want a location update from every node in every 100 milliseconds, right? How are you going to guarantee that? You can't guarantee that, because you have to sweep through all the devices, right? Otherwise you'll be unfair. Okay, so that is the limitation, right? So what is the alternative to this? What alternative should exist? Just use your common sense, right? What I have already there in this slide, this is enough. From this slide you'll be able to answer.
One control node is required, sir, here.
Okay, what is the control node going to do?
Like say it will means okay, it will synchronize all the nodes, sir.
No, but still what you are saying is at a more abstract level, right? So does it solve the problem? Does it solve my limitations?
Because it will allow only one to transmit at a time. Something.
Allow is fine. Let's say you are allowing it, right? Suppose there is a police officer who is telling me that, okay, only one guy is going to go through the gate at one time. Does it solve the limitation? Does it solve the problem? Because the problem will still going to be a scalability problem, right? You will not be able to handle too many devices, because for every device it will be a long time when you do localization for the same device. So if you, what is the time that you will take to localize this two devices, this one device successively? So location update 1 is going to come at t is equal to 0, and location update 2 is going to come at t is equal to maybe 1 minute. Does it solve the problem? It doesn't solve the problem.
Yes, sir.
Sir, maybe we partition the room into, or the area into several segments, and then we allocate some anchors to some set of devices.
That means a very good pointer, but what you are again assuming, you have to, if you are partitioning, these devices don't understand all this partitioning, right? It is a broadcast.
Yes.
So you are hinting that maybe you have to do a power control, right?
Yes.
Because, and or you have to, you will run in a situation of that exposed terminal, hidden terminal kind of problems, right? So
Yes.
so yeah, I mean that is possible, but there could be something simpler. Okay, because
Okay.
partitioning requires global knowledge, right? And that partitioning
Yes.
itself could be not a very trivial thing, algorithm to scale it up, right? So
Yes.
one idea would be, just why don't you reverse this device, let the devices receive, okay, and the infrastructure transmits. Because the infrastructure, the scale of the infrastructure is less. You have only 4 nodes, 5 nodes, 10 nodes, that's all, right? Anchors, right? Anchors, you don't have hundreds, maybe few anchors, 4 or 5 anchors you might have. They can take turn in transmitting, okay, and let all the devices here simultaneously. Okay, does it make sense? Because just this
Yes.
inversion actually makes the situation so better. The device, I would not say device receive, the devices receive. All the devices receive simultaneously. Infrastructure transmits now. But what is the bad part? We have to accept that now the device, it is the burden of the device to do the computation. Earlier, I was just participating in this ranging process, like I was just sending out the hello packet, and all the burden was taken at the infrastructure side. Okay, but there was a serious bottleneck about how much I can scale up. Okay, but in a situation where I will have hundreds of devices and they all of them, they are interested in knowing their location, then I have to rather use this kind of an architecture. The devices are going to receive and the infrastructure is going to transmit, and it is going to remove the scalability issue, because you will only have 4 anchors who will transmit. It will transmit at t is equal to t1, this will be t is equal to t2, t is equal to t3, and t is equal to t4. In 4 time slots I am done, and all the devices are going to get the location update simultaneously, right? So this is like GPS, right? So all the receivers, like any receiver in the vicinity, acquires these signals. Every receiver deduces its own location. Infrastructure need not be aware of the receiver's presence. Let's say I am running a shop, right, or like a big shopping mall. I have installed these anchors. I don't even want to know that whether there is some people who have come in my shopping mall or not. This is like completely privacy preserving also. All I am trying to do, I have these 4 time slots, 1 2 3 4. This is slot 1, slot 2, slot 3, slot 4. Just I am anchor 1 is transmitting again, transmitting. That's all. I don't care about anything else. No computation is taking place. I just want to make sure that I am transmitting in separate slots. Okay. And what this device is going to do, the device is going to know that what was the time taken, at what is the timestamp when I am receiving the update from anchor 1. Let's say this is at t1 prime. Okay, because it will not be t1, because it is a different time when the device actually receives the message from anchor 1, and it will be t2 prime, t3 prime, and t4 prime. Now it can do all sorts of combinations. It can do a TDOA, which is T1 prime minus T3 prime. Solve this equation. T1 prime minus T4 prime. T2 prime minus T3 prime. Right? So many range equations it can get. It's not a range equation. It's basically equation for time difference of arrival. Just solve for this, and on the device you are done. Okay. So that is a way in which you can massively scale up this system. Even if you have 10,000 nodes, doesn't matter. Okay. So that is one of the way, and it's very much like your GPS. And as I told you, it is completely privacy preserving. The infrastructure side have no idea about the presence or absence of this device. Okay. And now if the infrastructure tries to monitor you, then it has to be a different thing. Then you'll say, oh, you don't have to do any computation. Your device will be saved. You just have to. The device is very less complex. The device has to just send out a beacon, and all the hard work has to be done by the infrastructure side. And the infrastructure side gets a bonus. The infrastructure side now can poke into your privacy. It can know that where you are going through. Then the infrastructure side has to have some incentive, right, in doing that. Okay, so these are like 2 different ways you can implement time difference of arrival technique, TDOA. Okay, what kind of applications? What kind of applications you can have? As I told you, things like an airport or a shopping mall. Okay, where you want to give some kind of a navigation facility to users. Okay, and there could be other places in some specific small maybe retail stores where the navigation is not that important for the user. What is important is the location analytics of the user, right? So I want to analyze the location analytics, right? In those cases, maybe your device transmits, right? Device TX, that kind of an infrastructure might be better, right? And in that will be a more complex system, because as somebody told you, you need a controller who is going to tell you in which slot which device is going to transmit and so on, right? So that is a little bit more involved. Okay, and this is a little bit and then you also synchronize the anchors and so on. This is a little bit on the easier side to implement. Okay, so whether we have it today, we have all the things that I told you, right? Look feasible, but in terms of synchronization or in terms of the computation that has to be going inside the device, that could be also a lot, right? You also need a very good clock, right, for now you are not just taking the just time of arrival, you are trying to take the time difference of arrival, right? And if that number itself is very small, right? Because and then if there is a lot of noise in that difference, your errors will be more, right? So as a practical example, right, this is one of the a startup, right? I think it's an Estonian company who manufactures all such localization products, right? And they have a very clear explanation about why they still chose TOF instead of TDOA, right? So TOF, the time of flight, although it could be slow, it has to do this two-way ranging, but it is robust, it is stable, right? Whereas TDOA, time difference of arrival, might not be always the best solution. There are a lot of things that can go wrong with time, because from the very beginning in localization, I have told you the main primitive that you need to calculate is the time of flight. If that goes wrong, everything falls apart. Doesn't matter how sophisticated algorithm you have, if the time is wrong, the range is going to be very, very wrong, erroneous. And if the range is erroneous, your location is going to be erroneous. Okay. So there are some limitations, right? So assuming that we are having all the entities can overhear everyone, right? So I'm assuming that all anchors are covering this entire space. That has to be true. And sometimes that your infrastructure could also have to be sometimes listening, because it has to know that the other anchors are transmitting. For that time it has to keep quiet, and whenever the other anchors are done transmitting, when your device turn comes, you have to be transmitting, right? So just in short, right, these were the 4 slots that we mentioned. Okay, so this is that slot when let's say anchor 1 transmits, right? And whenever the next slot comes, the anchor 1 has to just listen. It is going to be in the receiving mode, and anchor 2 is going to transmit. All others are going to be in the receive mode. In the next slot, anchor 3 is going to be transmitting, and all of them others have to keep quiet or listen to the medium that somebody else is doing the transmission. So you have to continuously switch in between transmitting and receiving. Okay, and every anchor attempts to calculate its clock drift from the other. So this is more about the synchronization part. So either you can create a system that could be wirelessly synchronized, because see, the slot boundaries has to be synchronized with these anchors, and that is one of the main issues in TDOA, right? So everybody has to know that this is my turn to transmit. So you have to understand the slot boundaries very well, right? And these slot boundaries could be again in like very few or hundreds of microseconds could be, right? So there, like, clock drifts cannot be tolerated. So you have to always keep the system updated in terms of its clock. Okay, so now we have seen a lot of this distance estimation, both distance estimation and the difference of distance estimation. Now we have to look at other formulations, like what if we can get an angle, right? Because angle would always be very nice, right? Because if you know r, right, and if you know this theta, you can always get the location as r cosine theta, right, and r sine theta. So if you know the range along with the angle, then you don't need multiple ranges. Just with the angle and the range, you can resolve the location with respect to the anchor. Okay, so now we have to see, at least at a basic preliminary level, what kind of technologies exist to compute this angle. How can this angle be computed? And this is known as the angle of arrival. Angle of arrival. What is the angle of arrival of the signal? The signal is arriving. I knew the distance, like the time of arrival. What was the time taken by the thing to by the signal to come to the receiver device? Now I am trying to look at what is the angle that from which direction it came from. Okay. Also, I would say it is also known as direction of arrival. Okay. So one easy way, right, would be to look at directional sort of an antenna, right? Let's say you have a node, right, and you can, when the anchor is directed on the side, on this side as shown in with this arrow, right, you are going to receive a lower amplitude in terms of the signal strength, right? Suppose I am recording the signal strength here, recording the received signal strength with respect to the angle theta. So for this angle, the amplitude of the RSS is low. Okay, so then I actually steer the angle and it goes to this next part where the direction is a little bit more aligned towards the node, and it has increased a bit, right? Next, if you see this, it has really increased. It is actually the lobe of this beam is actually facing the node, right? And the directional antenna, what it does is basically it is going to cut off the radiation in the other directions. The radiation is going to be uh, beamed in a given direction. Okay, it is not like all the 360-degree angle you are going to be beam forming, right? It's not an omnidirectional antenna. If it is an omnidirectional antenna, then you will have the radiation in all directions, whereas if you have a directional antenna, it is going to be only focused, the energy is going to be focused in a single direction. Okay, and that comes with, of course, a certain concept of an angle. What is the beam width and so on, right? So let us assume there is some beam width. Okay, so beam width, but approximately, right, based on the value of the received signal strength, you can have a very good idea. Let's say here there was this maxima of this received signal strength here, so I know that the angle of arrival of the signal was actually at this is the angle. Okay, so in that way you can figure out the angle, but you require a directional antenna, and whatever we did was kind of known as mechanical beam steering, right? So mechanically, as if I have turned the direction of the beam, and in that way I am trying to see that what angle it maximizes the received signal strength, and in that way I can find out the angle in between my node and the anchor. Okay, so just remember that is the angle with the maximum signal strength. It is again going to die down. Of course, there could be issues, right? You can have a non-line of sight. So what happens if you have an obstacle here? If you have an obstacle here, you will not see this high amplitude. Maybe the high amplitude is here, and after that it goes down. Because at the angle where it is supposed to be having the maximum amplitude, at that particular direction there was an obstacle. Right? So sometimes it might not work, right? So the signal strength is always an inaccurate measure, right? And the signal strength in the vicinity, right? Even if it was beam forming in this direction or this direction or this direction, right? The signal strength could be very like very similar, very much correlated. Okay, so and then there is also some random noise that goes on in your path loss, right? What is path loss? The amount of power that the signal loses from the transmitter to the receiver. Okay, and this is the path loss that has some kind of random noise also associated with that, right? And what is the received signal strength? It will have some kind of randomness. So sometimes signal strength can become inaccurate. Overall it will be accurate, right? So the signal strength here is going to be very different from what is the signal strength here and what is the signal strength here. However, we are trying to narrow down, right? We are also, like the way we are trying to narrow down the range, in this case we are trying to narrow down the angle. The angle has to be as accurate as possible. Okay, so there is some other robust way in order to find out the angle of arrival, which involves multiple antenna setups. Okay, so now the anchor becomes a bit more complicated. The node, let it be just like a single antenna, right? And what the receiver, like what the anchor does, the anchor, instead of having a single antenna, might have multiple antennas. In this case, let us consider it has like a dual antenna anchor setup. Okay, so the main target that we are trying to achieve here is the measure the slight variations in the distances from the multiple antennas. So the claim is that the distance that this ray is going to travel cover, let's say from antenna number 1, is going to be different than the distance that will be covered from the node to this antenna number 2. Okay, so D1 and D2 will be slightly different, and that difference is going to be leveraged in order to estimate the angle of arrival. Okay, so let us go to basic geometry and something that you have learned also in physics, right, in waves. So if this angle is theta, that is what we are interested in, right? What is basically the extra distance that was that this particular ray has covered? So if this is, again, I come back to the same terminology, 1 and 2. So the ray of 1 has traveled an extra distance of d cos theta compared to uh, antenna number 2. Okay, so if this was d, this entire distance is basically d plus d cos theta, where d is the separation in between the antenna. Okay, the antenna itself are separated by a distance of small d. Okay, and note that this capital D is basically the distance between the node and the this is the node, right? And this, you can assume that it is far away, right? We can take the typical assumption that the rays are parallel because the node is actually far away. That assumption can be made. Okay, so typically it's basically is known as a path difference, right? So delta phi is like the phase difference. So the phase in which this the wave is going to come here is going to be different than the phase of arrival of the ray in this particular antenna, right? So for antenna 1, if you are having a phase of arrival which is phi 1, and in antenna 2, if you are having a phase of arrival which is phi 2, phi 1 minus phi 2 is going to give you delta phi. Okay, delta phi is what is the difference in phase, because this will be the signal, and I am going to receive the signal at a certain phase, right? If you just go back to this wave basics, right, that you study in like +2 physics, that multiplied by lambda, which is the wavelength, is going to give you 2 pi into the path difference. Okay, so this is your path difference. And what is this delta phi? This is the phase difference. In the receiver, it is possible to know the phase at which this was received. What is phi 1, what is phi 2, what is phi 1 minus phi 2. It is possible to know that value. You know what is the frequency that you are using for this system, so you know what is the wavelength, right? And you know d, right? Small d you know, theta you don't know. You want to solve for theta. Okay, so again, from a physicist standpoint, at this thing looks doable, right? Now how do you want to actually do this, right? In case of time of flight also, it was very simple. D is equal to time of flight into the speed of light. Okay, but then there is more to it. You have to build such a system that gives you an accurate angle of angle theta, right? And there could be certain uncertainties that is going to be there, right? And also remember, phase is going to wrap every 2 pi. It is again going to wrap. Time doesn't wrap, because time, it is always incremental. 5 nanoseconds, 10 nanoseconds, 15 nanoseconds, 40 nanoseconds, 100 nanoseconds. It is just going to increase. Phase is not like that. It is just going to go from 0 to 2 pi. Again it is going to go from 0 to 2 pi. You cannot find out the difference. Okay, so there are some minor challenges that are related to this. So let us say you partition this entire thing into 3 regimes. Okay, so one regime is d is actually smaller than lambda by 2. Lambda is the wavelength. Lambda is the wavelength of the signal. Okay, so if your d is really close to each other, the antenna distance is not very far away, lambda by 2, then there could be a situation where d is greater than lambda by 2 but less than lambda, and there could be a situation where d is really far apart from each other and the distance is greater than lambda. Okay, these 3 situations might exist. Okay, so let us see what happens correspondingly in when we try to calculate the value of theta, because d, if we know, right, we are basically trying to put this inequality where d is basically a function of lambda. We are trying to express the antenna separation as a function of the wavelength of the signal that we are using in the system. Okay, this is very important. So the physical form factor of the device or the anchor depends on the wavelength of the frequency, right? The device size, because if you want to manufacture this device, you have to place these antennas, and the separation among the antenna you have to keep in mind. It is going to be a function of lambda. Okay, you cannot just arbitrarily put antenna like this, because we are trying to see what is the implication of this distance. So if it is lesser than lambda by 2, just write that equation like in equation here, right? So delta phi lambda is lesser than equal to lambda by 2, because it is lambda by 2 into 2 pi cos theta. So what I can say, the phase difference is just going to be from minus phi to plus phi. Okay, so there will be no ambiguity. Okay, the phase difference is just going to be less than half. So in that way I can know that what is the value of theta. It is going to be from minus pi to plus pi. Okay, minus 2 pi to plus 2 pi. So it is like either the direction also I'll be able to tell you that it is basically going to pinpoint the direction of arrival. Okay, so if we go to the next case where it is greater than lambda by 2. Okay, so in that case what will happen is I again write down the same equation. Delta phi into lambda is now lesser than equal to, I just replaced it by the value of lambda itself, right? 2 pi into cos theta. Okay, so in that case what we can argue is again the value of cos theta is going to vary from minus 1 to plus 1. So it is just going to be minus 2 pi to plus 2 pi. So in this case this is half. I had a small mistake in telling you. So this will be minus pi to plus pi, right? So direction, right? So it is either going to be in this direction, right? So if you take this as an angle, so this will be like 0 to pi, or it could be 0 to in this direction minus pi. Okay, so if it is less than lambda by 2, it is there is no ambiguity. It can either be this, the angle could be this one, the angle could be this one, angle could be this one, anything, right? You can know what is the direction of arrival just using this two antenna system. And if you have more than that, if it's going to be less than lambda but greater than lambda by 2, it will be minus 2 pi to plus 2 pi, right? So minus 2 pi and plus 2 pi, it is going to have an overlap, right? So it can either tell you like this, or it can either tell you like this, right? So if you know what is the likely direction of the um, device, right, whether it is on the front side of the anchor or whether it is on the back side of the anchor, in that way you would be able to tell me the exact angle. Okay, but there is a small ambiguity. The ambiguity is not a lot, and often this ambiguity could be resolved by using a third anchor, a third antenna. So if you have one more antenna, that antenna could be used to resolve this small problem. Okay, then you can sort of think of trilaterate the direction of arrival. Okay, not exactly trilateration, but basically that the tiebreaker has to be resolved by some other antenna, that the third antenna can do that. But in a two antenna system, the takeaway point is that if it is greater than lambda by 2, we start seeing some ambiguity, and whenever it is greater than lambda, there will be so many ambiguities. Okay, because now delta phi is going to be from minus 4 pi to plus 4 pi. Okay, so there are many possible things that can come up here, and but it is going to improve the resolution. What will happen is there has to be some trade-off, right? Although there are an ambiguity, but since the distance in between these two antenna is more, this is going to have a better GDOP, okay, or a better resolution. Very simple, like common sense, right? If you are having the angle being measured from these 2 points and the 2 points are very close to each other, the geometrical diversity is very less. We also saw that in case of the drone. If the drone's aperture is very small, it is very difficult to find out the precise location of the node given the range errors, right? Here also in the phase calculation you will have some error, right? So I mean that is going to give you poorer resolution if the distance in between the two antenna is very small. However, it is going to have no ambiguities. But in this case, the resolution improves, you can find out the angle in a much clearer way, but there will be multiple ambiguities there. You have to identify which one of them is the correct value of the angle of arrival. Okay, and sometimes you can put more antenna. You don't have to limit yourself just to 2. You can have more than that, and that is going to help you in order to find out the exact direction of arrival. Okay, and yeah, so you can have an array of receivers, and this array can be used for doing this angle measurements, and this can improve your confidence. So maybe the first one we are seeing, this theta 1 is theta 2, theta 3, and theta 4. From this you can find out the angle in which the signal is actually arriving from. Okay, so this is also known as an antenna aperture. Okay, antenna aperture or antenna array. Okay, you have a series of this antenna, and from here you just apply the same set of equations and find out what is the angle of arrival for each one of them, and from there you can fuse this geometry to figure out the actual direction of arrival, right? And it need not be a linear array, right? This array could have any geometrical shape, and that is how you want to build this array, right? Based on the form factor of the device, you might have some limitations. You cannot make the device very large, right? Basically the anchor very large, right? And it also has an implication on the wavelength of the signal, right? So there are many of such factors that has to be taken into account while you are trying to engineer this array of receivers. Okay, so one common example is all this Alexa sort of things, right? That Google Nest and all, you have this at your home. They are selling this antenna aperture, which basically is not an antenna, but in this case is a microphone, right? So they are trying to find out the angle of arrival for voice commands. So you are saying, hey Alexa, do something, right? So they can actually pick up from which direction you are talking from. They have this array of microphones, right? And note that the separation in between the microphones, right? This is not like a random thing. This is highly engineered based on the wavelength of or the frequency of this human voice, right? Whatever frequency we are speaking in, that will have a corresponding wavelength, and that wavelength has to do with this distance separation in between the microphones, right? If you just take these microphones and put it in some kind of a this form factor, right? That is not how it is. It doesn't look like just like a CD, right? There is a reason why these distances are exactly this, right? Otherwise it will not be able to compute the correct angle of arrival. Okay, so they are having so many dual antenna setups, right? There will be 1 and 2, this 3 and 4, right? So you can take any combinations like 4C2. There could be like 6 2 antenna combinations, or in this case 2 receiver combinations, in order to figure out what is the angle of arrival. So fusing all such information, you can probably know that the person is actually standing on at a degree, let's say this degree, like let's say minus so this is minus 90, right? This is minus 180, right? Maybe some minus 135. So I can know from which direction inside the room is this voice command coming from. Okay, so and this also applies to even radio systems, right? Where the wavelength is just going to be different, right? So that is going to change the form factor of the device, because if you are making it too much larger than lambda, then you will have so much ambiguity you cannot resolve with just a few antenna or the few receivers, right? So you need to have a trade-off of the separation that you are allowing in between the receivers, and how much ambiguity you can have, or how much is the resolution that you are able to receive at, right? So if the separation was lesser, maybe the entire size of this antenna aperture is like a circle like this, right? So the angle would be more smeared. Okay, so the resolution is going to be poorer. Okay, that is the trade-off that you have to keep in mind while designing such array of receivers. Okay, so in this case, this is not a linear array of receivers; it's a circular array of receivers. Okay, and this is something that you can buy, right? Or there is a company called Seed. I think they use 3 E's for some reason. Seed Studio. They are going to sell you all this circular array of microphones, and you can program them. You can connect them to some microcontroller or like a Raspberry Pi kind, not a microcontroller. Maybe you will need a much more processing power. So you have to connect it to, let's say, a Raspberry Pi sort of a device, and then you have access to all this individual signals from each one of these microphones, which you can use to find out the angle of arrival. So that is like a nice exercise you can do, right? These kind of codes are all open source. Okay? Similarly, in case of your phone, often it is necessary that what is the direction that signal is coming from. Based on that, the beamforming could be made better. So in 5G, you also have to track the device location so that you can do an accurate beamforming. Okay, in 5G, I want to give more bandwidth, and we are trying to support multiple users simultaneously. So you have to know, instead of doing an omnidirectional transmission, I have to really know or accurately know what is the angle at which your phone resides, right? Based on that, I can locate it using such a technology, because see, this is like an antenna array, right? So this is an antenna array that you have inside this 5G phone, and this could be used to tell at what angle with respect to the base station my device is located, and the beamforming could be made very accurate. Okay, so even think about these huge receiver apertures where we are trying to find signals from outer space, right? We want to locate from which part of the sky there's a certain signal that is coming. We have this enormous area in which these receivers are kept, and this is an array of receivers, right? So they are always listening to any signals coming from outer space, right? So the scale has changed. The concepts, the preliminary concepts that I have told you remains very same. Okay, so with this we have looked at most of like the analytical portion of localization, that included time of arrival or time of flight, time difference of arrival, and angle of arrival, and how can all this data could be obtained, and what kind of algorithms that go behind them in order to build such systems. And also we looked at a real world example, like using this drone and UWB, about how to engineer a real system that takes these concepts, but you need to fine tune those concepts based on your needs. Okay, so now I will just ask if there are any more questions. We don't have a lot of time left. We had some discussion already regarding the UAV and things like that, but from the second part of the discussion, if you have any questions, please feel free to ask.